In this video, we're going to cover naming ionic and covalent compounds. So prior to this video, you should already know the mechanism by which an ionic and covalent bond is formed. That being, an ionic bond is formed between metals and nonmetals, the electron transferring from the metal to the nonmetal to create the ionic charges, which then brings them together, while the covalent bonds are formed by a sharing of electrons. Also important to note are the charges on the periodic tables of these ions when they become ions for group 1A, 2A, these select metals in the middle, and the nonmetals on the right side. Knowing that information, we can get right into naming ionic bonds. And naming the simple ionic bonds where you have a metal cation followed by the nonmetal anion. The way it works is the metal cation is named by its element name. So you just name the element. It would be for CaS, you would first name calcium. And then for K, it would be just potassium. For Mg, it would be magnesium. For the anion, you would have the name of the element followed by the prefix or the suffix IDE. You'd have an IDE ending on the name of the anion. So sulfur becomes sulfide. Fluorine becomes fluoride. Oxygen becomes oxide. So you're removing the last syllable and replacing it with IDE. And for this, for ionic bonding, you do not need to use prefixes, meaning di, tri, tetra, whatever the case may be. Those are only for covalent bonds, which we'll see. So here's some examples with transition metals. So with transition metals, it's a little bit different because those metals are the ones that occur in the blue part or purple part of this periodic table where you may not know their charges from looking at their group. So in this case, to the reader, the person who's reading the name, you need to denote what is the charge of the cation. So in that case, you would need to write Roman numerals. To do this, the Roman numeral would denote the charge of the metal cation, not the number of them there are. So for example, here you have FeCl3. This would be iron 3 chloride. The reason why is because chlorine has a -1 charge. There's 3 of them, meaning the total negative charge is -3. For a sufficient ionic bond to form, the positive charged cation has to balance out equal and opposite of the negatively charged anion, meaning the iron charge would have to be Fe3+, or otherwise known as iron 3. For iron 2 chloride, you see the difference, and there's 2 chlorines. For copper 1 oxide, in this case, the oxygen's charge is -2. There is 2 coppers, meaning each copper has to be +1 in order for the positives and negatives to cancel out. Therefore, each copper ion being +1 is called copper 1. So this would be copper 1 oxide. If you have CuO, then you just have one of each of the elements, one cation and one anion, meaning that the copper has to be +2, while our oxygen is -2. So that's how that works for transition metals. Now going to covalent compounds. These are a little bit easier because all you have to do is use prefixes to denote the number of the first or second element. So for example, an alternative name for water would be dihydrogen monoxide because you have 2 hydrogens and then you have 1 oxygen. The only thing that is different about covalent bonding, besides the prefixes, is that if you have only one of the first element, for example, just 1 carbon and carbon monoxide, you do not write the mono prefix in front of it. So you do not write this prefix. For every other number of the first elements, anything more than 1, you then write the prefixes. So for example, for the water, dihydrogen, it wouldn't be hydrogen monoxide, it would be dihydrogen monoxide. For CO, it would be carbon monoxide, and for CO2, it would be carbon dioxide. So just to refresh, what you're doing is you're naming the prefixes in front of the first element if it is only greater than 1, leaving the rest of the name of the element. And then for the second element, you are writing the IDE ending, again, just like we did for ionic, and this time adding the prefix for the number of that atom or element. So let's do some practice. These are some practices with some ionic bonds. And first thing first is to recognize if they're ionic. Calcium, barium, sodium, aluminum are all metals, and then the anions are then listed here. So calcium carbide. So calcium we know is a +2. Carbide means it's carbon, so it would be carbon is actually -4. So the only way for this to work out would be Ca2C. because the positive charge from calcium would be +2 times 2. Pairing that up with one carbon of -4 would then make the ionic bond satisfactory. For barium, we also have a +2 charge. And for nitrogen, the nitrogen ion nitride would have a -3 charge because it's located in group 5A. So for this, we can use our crisscross rule, or we can use our least common multiple, however you want to think of it, to see how many bariums can cancel out with the number of nitrogens. And if you did a crisscross rule, or you just said, all right, if 3 bariums are here, we would then have +2 times 3, which would be +6. And if we had 2 nitrogens, which would be 2 times -3, you'd have -6. So this means our formula for barium nitride would be Ba3N2. That crisscross rule I mentioned, all that means is you can take the charge after you write the ions and just cross it to the adjacent atom. And this would actually work out for most cases. But it would not work out for the case we just did, calcium carbide, because if you did that, you'd end up with Ca4C2, which technically isn't correct. For the next one, sodium phosphide, we can do the same thing, Na+1, and then phosphorus is P3-. If we did the crisscross rule here, we would get Na3P. And that works out mathematically because we have 3 sodiums, so it would be 3+, and then you'd have 1 phosphorus, which would be 3-, and then that would work out. For aluminum sulfide, aluminum would be a 3+ charge. Sulfur is a 2- charge. So we can also do the crisscross rule, and we end up with Al2S3. And mathematically, this checks out because we have aluminum is a 3+ charge. There's 2 of them, so that's +6. And then there's 3 sulfurs, which are -2 each, which would be -6, and that cancels out. So let's do some practice with some transition metals. Now here we have titanium chloride, some kind of titanium chloride. So we have chlorines, we have 4 chlorines, and each of them are -1. Therefore, the total negative charge is -4. Titanium would then have to be +4. What that means is the charge of each titanium is +4. So you'd have titanium 4 chloride. Next one, PbBr2. So bromine is also a -1 charge. There happens to be 2 of them, so -2. Our lead would therefore have to be +2. So you have lead 2 bromide. For the next one, we have Fe2S3. We have sulfur, which would then become sulfide, and sulfur has a -2 charge, but there's 3 of them. That means we have -6, and then we have another +6 situation here, which means each of our ions, since there are 2 of them, each of our ions has to be +3. So we'd have iron 3 sulfide. Now moving on to polyatomic ions. For polyatomic ions, basically this means there are ions out there that consist of multiply bonded covalent bonds, multiply bonded atoms that can be used as a unit of an anion, or most of the time anions except for ammonium, which is a cation. These are some of the common polyatomic ions that you should know, and they each have a specific formula and a charge. When naming with these polyatomic ions, you just write the name of them. There's no need to change the name to an IDE ending or anything. So for example, if you have NaNO3, this would simply be sodium nitrate. NO3 is nitrates right here, so it would be sodium nitrate. If you had PbNO3 2, you would have lead 2 nitrate. So you wouldn't change the name of the polyatomic ion at all. Some of these polyatomic ions have sequences of adding oxygens, meaning for the chlorate ions, there are 4 of them, and it's pretty easy to memorize once you understand the hierarchy in terms of oxygen number. So you have hypochlorite. When you have an ITE ending, that usually means there is less oxygens than the ATE ending. So you have hypochlorite. Hypo means less than. So it's less oxygens than chlorite. Then you have ClO2 negative, which means chlorite. So you have hypochlorite, which is one less oxygen than chlorite. Then you have chlorate, which is one more oxygen than chlorite, which is ClO3. Then you have perchlorate. So per means greater than. So it's the most high on the list of chlorates and chlorites. So the little mnemonics like this and things to remember the polyatomic ions are key. And you see that 8-ite ending happening in a lot of different polyatomic ions. You have nitrate, which has 3 oxygens, and then you have nitrite, which has 2. You have sulfate, sulfite, carbonate, carbonite's not here. There's some other ones too, phosphate and phosphite. There's a bunch of them. So let's try to name these combinations of ions and polyatomic ions. So here we have an ion at aluminum 3+ with sulfate 2-. And what we do is very simply, we do the crisscross rule just like we've been doing. So we have aluminum 2, SO4 in parentheses this time, 3. So we have 3 sulfates cancel out with 2 aluminums based on mathematically the charges of the cations and the charges of the anions canceling out. And this name would be aluminum sulfate. The next one, this is hydrogen carbonate, and this is chromium. So we'd have, before we write the formula, we'd have chromium, hydrogen, carbonate. So you simply just write it like that. These are the easiest ones to write their formula, or to write their names, excuse me. For chromium, we have 2+, and for hydrogen carbonate, it's 1-. So the formula would be needing 2 hydrogen carbonates to cancel out with 1 chromium. Here are some covalently bonded practice problems. So you have dinitrogen tetroxide. Dinitrogen means 2. So you have 2 nitrogens. Tetra means 4. So you have 4 oxygens. These are very simple compared to ionic. Sulfur is just 1. Hexafluoride, so you have 6 fluorines. Diarsenic, so you have arsenic, which is As, and you have 2 of them. Trisulfide, which is S3, so 3 sulfurs. Now let's move on to naming acids. So naming acids is an easy scheme once you know the polyatomic ions associated with the acids. So acids have anything, or really anything that has an H in front of it. That's the general chemistry way of knowing them. And the question you need to ask yourself is, does the anion contain oxygen? We're looking over here. If the anion does not contain oxygen, meaning it's monatomic or it just doesn't contain oxygen, like cyanide, for example, then you have to use the hydro prefix. So this is hydrochloric acid because, look, the anion is just chlorine. And same thing for bromic, for hydrobromic acid. Bromine does not have an oxygen onto its anion. So you would just have hydro, then the anionic root, then you would change the ending instead of IDE to IC. So if you have HCl, that would be hydrochloric acid, not hydrochloride acid. Same thing for hydrobromic acid, hydrocyanic acid, and other things like that. If you have an anion that does contain oxygen, which a lot of them do, such as nitrate, nitrite, sulfate, sulfite, you then need to look at the ending of that polyatomic ion. So if we look at, check the ending of the anion. If the polyatomic ion ends in ITE, meaning ite, so that means your nitrite, for example, then you have to add the suffix OUS. So you have to remove the ITE and make it nitrous. So if an ite turns to us, ite turns to us. And then you add acid at the end. So sulfite turns into sulfurous acid. Then when you have ATE, meaning nitrate or sulfate, the ATE ending turns into IC. So that means sulfate turns into sulfuric acid. It's kind of different with sulfate because you have to change it more than one syllable. But for nitrate, it would turn to nitric. So that one works perfectly. So that is how you name acids. And here are some names of some of the acids. This is NO3. So you have HNO3, which is nitric acid, which was nitrate to nitric. NO2 is nitrite. So you have HNO2 is nitrous acid. H2SO4 is sulfuric acid because SO4 is sulfate. So the 8 turns to IC, turns to ic. SO3 is sulfite. And that means the ending then turns to OUS, so sulfurous, and so forth. So we can look at some examples here with the chlorates and chlorites examples, where if we turn hypochlorite into an acid, the ITE turns into OUS. It would be hypochlorous. The chlorite with an H in front of it would turn to chlorus. The chlorate would turn to chloric. And then the perchlorate would turn to perchloric once you add these hydrogens in the beginning. So that's basically how you name acids. And we can do some practice right now before we finish. So H2S. This is a polyatomic. This is not a polyatomic ion, but it doesn't have oxygen in it. So this means we have hydro sulfuric acid. So there's a difference between sulfuric acid and hydrosulfuric acid. The hydro means that you have just H and you don't have a polyatomic ion that has an oxygen in it, because that's where we get this naming scheme from. Then you have HClO3. So ClO3 is our chlorate. So this would be chloric acid. Then you have HNO2. NO2 is nitrite. Then you have nitrous acid, because the ITE, according to the chart, turns into an OUS ending. So it would be nitrous. And then to summarize, here is the rules for naming ionic and covalent bonds. And I hope you enjoyed the video and learned something. Please like and subscribe.